I'm going to show you my solution for the assignment of analyzing a single coil permanent magnet brushless motor. This is for the purpose of ultimately having a physics model for the Mendocino pulse motor, but we're analyzing the simpler case here, or more familiar case, where we have a single coil that is rotating in a constant B field. There are no brushes, so that's why we call it brushless. We apply either a voltage across the coil or we drive a current. If we're going to drive a current, then we're going to use 10 milliamps. If we're going to drive a voltage, we're going to assume 1 volt. We also are going to assume an operating point, a rotational speed operating point of 2 pi 80 hertz at this point. Some of the results may actually investigate changing the rotational frequency, but if not, these are going to be the these 3 entries here, the 10 milliamps, 2 pi 80 hertz, and 1 volt are going to be the 3 operating points. You see some of the other system parameters here. I've chosen them so that they try to mimic as best as, within reason, our actual Mendocino pulse motor. Okay, so I won't go over all the theory here because we've talked about it in person, but I'll scroll through here so you can actually see my solution. Primarily we're looking at, Lorentz forces that are going to be acting on the coil due to there being current flowing through those coils, or that coil, in the presence of a magnetic field. It turns out only the coils, only the sides of the coil that are normal to the magnetic field, where we see the force down and the force up, those are the only 2 sides of the coil that actually result or have a force that acts on them that tends to rotate the rotor, or the coil. And you see the result here. It's a function of theta m. The theta m is the angular displacement of this motor. The coil currently here is in a angular displacement theta m of 0, and positive theta is when it rotates counterclockwise. Okay, my rendering is really poor on here. Okay, so we can calculate a final form for the torque. That is a function of the position of the rotor, or the coil, and the coil current. And that is equal to coil current times a motor constant that is defined right up here. I just basically got rid of the turns, the B field, and the cross-sectional area of the coil, which came about from Lorentz's force calculation. We're going to roll that all into one constant. That constant, by the way, has units of Webers, volt-seconds. And then the torque is going to be proportional to the cosine of the displacement angle, theta m. Okay, that's our first equation. Second one is that we can calculate the the flux cutting through the coil, and that's going to be a function of the sine of the theta. It's the magnetic field intensity, or density, times the area of the coil. And so we see that that is a function of theta m, and it's a sine as opposed to the torque being a cosine. But by Faraday's law of induction, we have the coil voltage is equal to N d phi dt. Now, Faraday's law shows a minus sign, and I'm not going to go into why the minus sign is not here, but if depending on how I label the polarity of E coil, on my coil, I could have the minus sign or not the minus sign. Now, someone could argue that I did it improperly in terms of the convention that I used, but in the end, it is correct, though one may complain that it's against convention. It's correct because I have appropriately labeled the polarity on my coil. I didn't mention that here, but the positive of the coil is the red and the negative is the blue, and positive current enters the red and comes out of the blue. So I'm using passive sign convention for the coil. Passive sign convention is one where the positive current goes into the positive labeled voltage node. Okay, and what results from that is if you have a positive current and a positive voltage, the product is a positive power, and that power is interpreted as power that is being delivered to that element, being absorbed by the element. So passive, meaning or implying that we don't expect to get any energy, net energy from this device. We plan on delivering energy to this device and net energy to this device. Of course, a motor like this can act as a generator or as a motor. We're using it as a motor, so it's appropriate to use the passive sign convention in this case. So based on Faraday's law, we can come up with the induced coil voltage, which is turns out to be the motor constant times the angular frequency times cosine theta m. And we note that just like we had a cosine theta m in the torque, we have a cosine theta m in the coil as well. So E coil and torque coil are in phase with each other. Now we write E coil as a function of omega m and of the position. We need both. Now and of course you can get omega m from taking the derivative of theta m with respect to time. But I've chosen to list them both explicitly as arguments to the function. Incidentally, we can write the following expression here. So notice that the torque exerted on the coil and the Faraday induced voltage in the coil are proportional to each other. Okay, so I just mentioned that they're in phase. So if I take the torque of the coil, the expression equation 1 above, and I divide it by equation 2, then what I get is E coil over omega m, because the motor constant kb and the cosine theta cancel out. And I can now rearrange these where I move to the left side omega m multiplied by torque, and to the right side I have I coil times E coil, and we see that power is conserved. The electrical power going into the system using passive sign convention in the way that I've labeled it, the E coil, I coil, both being positive means there is a positive power going into the motor, and the choice of convention or polarity for tau and for omega m is such that when those are positive, those are actually kind of active sign convention, so that it's power going out to the mechanical system, essentially the rotational inertia, any viscous or any Coulomb loss or load that might be attached to the rotating shaft. Okay, so whenever you have an opportunity to show conservation of energy, then it's good to look at that. Okay, now we want to look at the current, the coil current as a function of the applied voltage. So this, in the previous exercise above, we expressed torque as a function of current. Like I'm going to push a certain amount of coil current. Doesn't matter what the coil resistance is. I'm going to just push a certain amount of current. Now we're not going to push current. We're going to apply a voltage, and we're going to see how much current results. So the current that flows through the coil is going to simply be the voltage across the coil resistance divided by that coil resistance. And the voltage that's across the coil resistance is going to be the total externally applied voltage V coil. So V coil is the voltage that's literally between the red and the blue, the two orange rings here, if you will. And I'm going to take that, I'm going to take that, where did we go? Yeah, we're going to take that voltage, subtract the E coil, the induced voltage, K omega times cosine theta m, and that's what we have across the resistance. We'll divide that by the resistance to our current. Now we can use this current in our above torque expression, and when we do that, we can now express torque as a function of coil voltage, external coil voltage V coil. So this is like your motor voltage Vm, We also add in omega m now because the induced voltage, Faraday voltage, is a function of omega m, right? It's kb omega m times the cosine of the position. So now we have this expression for torque as a function of angle theta m. So that's our fourth expression. Now we want to look at power, the electrical power in and mechanical power out. Hold on. Okay, I've gone to the PDF because the MathCad was getting corrupted. I don't know if it's with the video recording at the same time, but it was having rendering problems. Okay, so now we're going to look at the electrical power in and mechanical power out. Electrical power in is just V coil times I coil, and we can write that the V coil is actually equal to the EMF voltage or Faraday voltage plus the voltage across the coil, which is R coil times I coil. All of that is times I coil. The mechanical out power is just the torque delivered by the coil or to the coil times the rotational frequency omega m. So we can write those two expressions as equations 5. Now these are as a function of current, okay, I coil, but we're really more interested in expressing them as a function of voltage because after all we're going to be applying a voltage, not applying a current. The current will be the response. So the electrical power in this case is still V coil times I coil, but I coil will be equal to, like as we did before, the external coil voltage minus the internal Faraday voltage, E coil divided by R coil. The mechanical output power is still going to be the same. But now when we express these, notice that in the arguments we no longer specify I coil, we specify V coil. So we can express these two powers as a function of the angular position, angular velocity, and the externally applied coil voltage. These are equation 6. Now number 7 is where we're actually going to look at the energy. So we're going to integrate the power between two angles, and instead of kind of deciding those a priori, we're going to actually put those in as arguments from theta O to theta m, and we're going to calculate the amount of work. Notice that we're integrating with respect to theta, and so you can relate d theta and d time by omega m, and so that's why you end up getting a 1 over omega m out in front here, and that allows us to integrate with respect to theta as opposed to with respect to time. Okay, now again these were expressed as a function of current here, but the ones we really want to use are going to be expressions that are as a function of V coil, and so that's what step 8 is here. We express them, the input work and the output work, as functions of V coil along with angular frequency and a range of angular positions. And you'll see here in a minute why I chose to pass those angular positions as arguments. So now we're ready to look at some results. So starting back from the first equations and kind of moving through that, I've plotted everything here just to, for a visual. So we're plotting motor coil torque as a function. Everything here is going to be as a function of rotor position. And the zero angle, maybe I should go back, the zero angle is this angle right here. Okay, so at an angle of 0, the flux through the coil is 0, and if we also look at the torque applied to the rotor or to the coil at this point, it'll be maximum. Notice it's this scenario here. So we have the force pointing directly up and pointing down, and that force now is actually at a right angle. It's normal to the torque arm, so we get maximum torque at this point, and we should be able to see that in our first plot. So here's the units are millinewtons, millimeters. okay, or it would be Newton meters times 10 to the minus 6. So it's maximum at an angle of 0, and I'm plotting here theta over pi, so this is pi over 2, or 90 degrees. And we see that the torque is 0. Basically, it's positive for a range of pi, or a range of 180 degrees, centered around the angle of the 0 angle. And then for the other 180 degrees, which are the pi over 2 on the right side and pi over 2 on the left end, the torque is actually negative. Of course, this is why we need to have brushes on a normal DC motor, because after you rotate half a revolution, you need to commutate the windings and drive the windings in the opposite polarity, so that you can produce a continuing positive torque. It would basically take this negative segment and flip it up here, and flip this one up, so that you end up having positive torque the full way around. In our case, we don't have commutation. We don't have any commutator, right? So it's incumbent on the drive circuit to actually shut off the current to the coil once you get out here to 90 degrees or minus 90 degrees. And the best you can do is not energize the coil during the outer 180 degrees. If you have another coil in the system, then you could power it, during that time. And that's what the brushless DC motors do. They have multiple windings, and they power alternate phases at different positions through an entire revolution, so that you always are contributing a negative positive torque to the motor. Okay, number 2 is where we're plotting the EMF voltage, and notice that the voltage, the induced voltage, they're both cosine functions, so they are both maximum at 0 angle. And this should make sense, because if you think of where there's a maximum change in flux density or flux through the coil, it's when the coil has 0 flux through it, right? It's the 0 crossing of a sine or cosine wave, and so that's where the slope is maximum. Okay, and going on to 3 now we're going to look at the coil current. If we apply a voltage of 1 volt and we're rotating at 80 radians, 80 times 2 pi radians a second. Okay, and here we see that the current is actually minimum at 0 degrees, and that makes sense because the voltage is actually maximum. So 1 volt here is what we're driving across the motor coil, and the induced voltage is up here at whatever, 0.75, so we only have 0.25 volts that's going to be applied across the coil resistance, and that's what's going to drive our current. So that should make sense. All right, now we're going to look at the coil torque versus angular position, and we're looking at it both for a constant coil voltage and for a constant coil current. So we looked at it already with the constant coil current, but we're going to plot it here just as a reference point. It's the dashed line here, the orange dashed line. So recall that the torque previously for the constant current was nice sinusoid. It was actually a cosine function. Now we see that the torque, when we apply a constant external coil voltage, we have a torque that is actually somewhat constant over the range of minus 90 to plus 90 degrees. Granted, it gets to 0 right at 90 degrees, just like the constant current one does. But it has these lobes out here that maintain on a broader top, if you will. Okay. However, when you extend past the minus 90 or plus 90 degrees, now the negative torque grows much more rapidly and becomes much larger than just pushing a constant current. So there's benefits to driving a constant voltage across the coil between the minus 90 and plus 90 degrees, But you need to be very careful that you quickly cease to energize the coil with that voltage when you get beyond minus or plus 90 degrees, because the torque becomes very large and negative, and that would basically you'd be extracting energy from the rotational system at that point and using the motor as a generator, which is not what we're trying to do here. Okay, now we're looking at input power and output power. So electrical input power and mechanical output power versus the angular position at a constant coil current. So again, this is our starting point, but we're not actually going to run the motor this way. And we see that the electrical power in is greater, of course, than the mechanical power out, and the difference between these two will be what is lost in the system. And in this case, the only place that we can lose power is in our resistor. Recall that we're not modeling the frictional losses or anything. Any output power, mechanical output power, the orange here, that power will actually ultimately go to feed the rotational losses, static or Coulomb or viscous. We note the magnitude here of the power. We're on the order of 10 milliwatts input. Now this is instantaneous, so the average input power, if we were just driving during this minus 1/2 to plus 1/2 pi, and we did that for basically 180 degrees and did nothing for 180 degrees, we could say that the average input power was basically the average of this sine wave over that period, and then divided by 2, because we only do it for half of the full cycle. So maybe we'd be somewhere around, 7, 8 divided by 2, maybe 4 milliwatts of input power. So now let's look at the constant voltage case. This is the case that is representative of what we're actually doing in our system. So we're applying a constant 1 volt. We're still using a fixed 80 times 2 pi radians per second. And now we see the input power is this blue. And again, the input power will always be greater than the mechanical output power because there's some power that's going to be lost. Notice first that the scale is different from before. We're up to 50 milliwatts, whereas previously we were topping out at about 11. So, this is down here, which is not labeled, is probably closer to the 10 milliwatts or so, 11 milliwatts. So what we notice is that the mechanical power out has this broad top, as we'd seen before, which is better than the pure cosine, right? We actually broaden this. We're able to deliver mechanical power for a wider range of angles of the full plus and minus 90 degrees. But there's a penalty, because we notice that as we move away from 0 degrees, the input energy or power goes up significantly. So for instance, if we go over to very close to minus 0.5 or minus 90 degrees, our input power there looks like it's close to 35 milliwatts, and yet at that point the actual power, mechanical power going out, is 0. If we move a little bit to the right, maybe we have some output power, mechanical output power, that's 1 milliwatt or 2 milliwatts, but we're having to contribute maybe 30 milliwatts in. So in this region here, out of these skirts, if you will, near the plus and minus 90 degrees, the motor is very inefficient. Whereas right here in the middle, where the input power goes close to the output power, our efficiency is much higher. And I think the efficiency is the ratio of these two. Okay, so maybe right here we can get close to 80% efficiency. Obviously here we're at 0%, and if you operate over this whole range, we'd have to take the integral, right, of that power over the period, or over this period of time, and take the ratio of output energy over input energy.